Hi, in this chapter we're going to cover atmospheric moisture and weather. This is chapter 7 and 8 according to my book. So there's three different phases or states of water. We've got ice when it's solid, liquid when it's a liquid, and gas, or the term sometimes used as vapor. So temperature is just a measure of kinetic energy, how fast essentially the molecules are moving. We get something called absolute zero. That means there's absolutely no movement whatsoever. So we can look at the hydrologic cycle. This is basically the circulation of water on the earth. We have condensation, precipitation when it falls from the clouds to the sky, or clouds to the ground. We've got evaporation, evapotranspiration from vegetation and soils, or from energy from the sun that creates clouds. So you can see this whole process. We've got runoff, i.e. rivers, but we've got groundwater. So when it hits the ground and it percolates and infiltrates into the ground, it eventually makes its way via gravity, just like rivers do. So we have evaporation, and it's basically changing from a liquid to a vapor, a gaseous state. We have different volumes. Hotter the air, the more capacity air has to hold and retain water in its vapor state. So warm air can hold more water, cold air holds less water. Okay? And that's going to be really important when we look at one of these formulas here. So when we look at this chart, we can see how much it can hold. We have something called relative humidity. And a lot of times, some of the terms we hear on Weather Channel or whatnot talk about relative humidity. How much can it hold for that particular temperature? So it's 100 because it's a percentage times the actual humidity, how much it has, versus the saturation humidity. How much can it hold at that particular temperature? So I have a volume of air, specific humidity 14, the air temperature is 25. I use my chart, so it's just 14 over 20, which is 70%. This is going to be important. Antarctica. We have a mass of air whose temperature is 0 degrees. It can only hold 4 compared to 20 previously. And it's 75% relative humidity based at that temperature. And you can see the relationship between relative humidity and temperature. To me, the important thing, or the interesting thing, is what happens, and we'll talk about orographic precipitation, but we have clouds here. Okay, and basically clouds are just when we get to getting close to 100% relative humidity. And we've got fog, and this is when it happens at the closer to the surface. And a lot of times you will see these over water when we get to 100% relative humidity because of changes in temperature, either in saturation humidity or in specific humidity. Okay. This example right here on the lower left, this is what we call orographic precipitation. So as air moves up a slope, what happens to its ability to hold the water? It decreases. So remember we looked at that 14 over 20. It gets pushed up a slope because of winds or whatever. And we know that as we go higher in elevation, temperature gets lower and its ability to hold water decreases. So we get to 14 over 20, 14 over 19, 14 over 18, 14 over 17. And eventually when we get to 100% relative humidity, we've got to get rid of that. We can't be over 100% relative humidity. So we have the formation of clouds or whatnot in these particular instances. Same thing with cooler water. We've got some air mass that moves over water, which is cold. Its ability to hold water decreases. So we have different types of fog. We have advection fog, and this is the distribution of fog in the continental U.S. and southern Canada. And you can see the spatial distribution of these, and how might they affect car accidents or whatnot. So you can see it's really high here. We have mountain range here. We have mountains here. Right? And this is the example that I talked about with. This is called orographic precipitation. And this is just one example of the precipitation that we're looking at. We have weather, okay, and these are typical winter weather air mass locations around the U.S. I alluded to this before, but we have different air masses that form over water that are warm, air masses that form over land that are cold, air masses that form over water that are cold. So these are called MP, maritime polar, and they have different amounts of heat, humidity. We have CA, continental Arctic, so they form over continents. They're going to be very cold. You can see the specific humidity attached to those versus your maritimes versus your maritime polars, or your maritime tropicals rather. Okay, so in summer patterns, we've got these CP, continental polars. We've got a continental tropical. I see it's kind of interesting where all of these different air masses meet in the middle of the United States. And what do we have in the middle of the United States? Tornadoes, instability or whatnot. Okay, I think about 97% of all tornadoes in the world occur in the United States because we have the mixing and meeting of these highly different and volatile air masses here. So, and we have topography, so the CT and the MT, they move across the continent because there's no topographic barriers, but a lot of times these maritime polar air masses, they're going to hit mountains here. We've got the Cascades here, we've got the Rockies here. Okay, so you can see the distribution of some of these air masses. Okay, I mentioned before about lapse rates. And then adiabatic lapse rates refer to non-saturated dry air versus lapse rates, and just the slight difference between them. For your unstable and your stable air, but we know that as we go higher up and we go up in elevation, temperature decreases. But if it's unstable, it wants to get to equilibrium. So we've got indications of stable atmospheres versus unstable atmospheres, your dry adiabatic wet rates, adiabatic rates, but your different lapse rates here. And you can look at examples of your stable air. Stable air wants to stay down, unless it's forced upward by a force such as a cold air mass that bumps it upward, or perhaps mountains or whatnot. And then you can see the precipitation patterns topography right here. This is a cross-section of Oregon, so we've got something called the Coast Range right here where we have a little bit of precipitation, and then we have the Cascades here, which are really high, that form a lot of your orographic precipitation, and then when you get to western Oregon or western Washington, it's literally desert. And so you can see examples of it here. So we've got this coast range that I talk about. We've got the Cascades that get rid of the last of the precipitation. And then essentially we've got desert. We do have mountains over here. These are called the Blue Mountains, I believe. And you can see a perfect example of some of this orographic precipitation, or what we call orographic lifting if there's not precipitation involved. We've got cold fronts and cold fronts and warm fronts that act the same way. Cold air is going to be more dense than warm air, so it's going to push warm air up. When we push this air up in a cold front, its specific humidity is going to stay the same. Its saturation humidity is going to decrease until we get precipitation at that front. And so you can see this wedging here. That was sometimes the term we used in the formation of clouds. Cumulonimbus, your thunderclouds. And the same thing with your warm fronts here, which are going to be less drastic. And you can see the symbols here for your cold fronts, your warm fronts, your stationary fronts, where they're basically not moving against each other until acted on by another force, and then the kind of movement of air and fronts and whatnot from different directions and how they interact with each other. And you can start to see how these interact with your isobars and your barometric pressure. we can see a station model. So this is the basis for weather mapping. You can see the wind direction, remember where it comes from, the temperature, dew point. There's a number of different symbols that tell what it is. Sea level pressure. Okay. Typical pressure is about 1,000 or 993 millibars. So you can see this is slightly high pressure. It's rising. Precipitation. So you can tell a lot of different things with some of these station models. Some of these are going to be abbreviated or whatnot. We'll see examples of these here. You don't see all the symbols there, but you can see the temperature and the weather patterns, and then you can see the wind speeds and the wind directions attached to these. And this is for the western United States, and this is for the entire United States. And so you can see the current temperature, and then the dew point, and that's the temperature to which the air must be dropped to have 100% relative humidity. So if they're close together, that means that high humidity, like 66 versus 61. If it's further apart, 54 versus 36, it's going to be less humid air. And then you can see your storm tracks in general in the United States. We work from west to east. And then you can see the satellite conditions, and then what these station models mean. And these cyclonic circulations and moisture supplies. Violent weather, we've got thunderheads or thunderstorms. Lightning is the visible flash. Thunders accompanying lightning with the explosion or the expansion of air. And then hail. Macrobursts, microbursts. And you can see, with the freezing level here, this is situations or scenarios where we would have hail, where we have this uplifting, it's so strong that it keeps hail aloft, so it accumulates layers of ice, and then until it gets big enough to fall. You can see squall lines, where we have these very severe fronts. Twisters, tornadoes. Where we have this instability. They typically occur in the central U.S. And you can see a map of the total number here. So we can see a nice map. Texas, believe it or not, Florida have a lot of them. A lot of times because it's flat. And then down in the bottom corner we can see where they are. But here's a nice map that shows spatial distribution of these over time. And they're measured using the F scale, F0 up to F5. And we've got tropical cyclones. Okay. So these are your cyclical patterns. So we've got hurricanes over in this neck of the woods here. They're just called something different, typhoons versus cyclones. And I believe they're measured using the Saffir-Simpson hurricane damage potential based on wind speeds, storm surge, Category 1 up to Category 5. And you can see some of the wind disasters here, especially along the coasts here, due to hurricanes. Okay. And a lot of times where it intersects with geography is that people like living along the coasts. So when we have these sudden changes to sea level or hurricanes or whatnot, it affects these people living along the coasts here. Whether it's Sandy in 2011 or some of the other recent ones we've had. Okay. And these are just some examples. Here's a cross section with the eye and the eye wall. This was my house in King William County in 2003 as a result of Hurricane Isabel, if I remember right. I came home and this is what was sitting on my house. And we have different bands, the eye, which is clear, and then you can see the paths of these. And every year they generally take these paths. Some of them get close enough to get to the United States. Most of them kind of peter out in the middle of the Atlantic. And you can just see some of these, what they look like, and the intensity attached to these. I think I have a lot of these here. and you can see what it does to some of these barrier islands. For the most part, Virginia Beach, the city of Virginia Beach is just located on a little one of these barrier islands, and there are some bays that go behind it, especially as you go further south down in North Carolina. And you can see how temporary these are. Last thing we have is weather, current state of the atmosphere, monitoring stations, satellites, and whatnot.